All right, welcome. This is going to be section 5.1 and 5.2. We will be graphing linear inequalities and we will be shading. Yay, right? Get to use all the fun colors today. Okay, so linear inequalities in two variables generally describe a half plane when graphed. Use the following steps to graph a linear inequality in two variables. Use the inequality to write a linear equation, which serves as a boundary for the graph. Means when we're about to graph it, let's change the inequality into an equal sign so we can solve for X and Y intercepts and whatnot. 2, if the inequality sign had a less than or equal to or greater than or equal to, then the line will be solid. If the inequality is less than or greater than, the line will be dashed. And after we're done graphing, we are going to pick a test point. And you're going to pick a test point on either side of the graph. Nothing on the line, but either opposite side of the line, above the line, or below the line. So that's where we'll pick a test point. We never pick test points on the line, okay? And whatever side holds true, you'll shade. And if you pick a test point that is false, then you will shade the opposite side. Okay, so let's get started. Example 1, y is greater than x plus 1. Okay, y is greater than x plus 1. So our first step is to make it into y equals x plus 1. Y equals x plus 1. Okay, well, this one's going to be pretty straightforward to graph. We can look for, we can use the slope and the y-intercept for this one, right? So if we look at it in this form, y equals mx plus b, the slope from the original equation happens to be 1. And the y-intercept is also 1, which we translate into a point, 0, 1. Okay, so now the next part is to notice your inequality. We want to know, are we going to be a solid line or a dashed line? So looking at our inequality here, it is just a greater than symbol. So 2, we're just going to say we'll have a dash line. Okay, we'll have a dash line. So let's go ahead and graph. I have a y-intercept at 0, 1. Let me see what's going to be the best. There we go. All right. I have a y-intercept at 0, 1, which is right there. And then my slope happens to be 1. So that means we're going to go up 1, over 1, up 1, over 1. So up 1, over 1 there, up 1, over 1 there, up 1, over 1, up 1, over 1, up 1, over 1. And then I'm going to go down 1, over 1, down 1, over 1, down 1, over 1, down 1, down 1, down 1, down 1. All right. And now let's just connect our points. And remember, our line is going to be dashed. So okay. Now the next thing is let's pick a test point. So that's going to be step 3. Let's pick a test point. I'll do that here. I'll say 3. Test point. And when we pick a test point, we choose a number, a point above the line, or we choose a point below the line. So we can choose any of these points or any of these points. it does not matter, as long as you don't choose a point on the line. And sometimes the easiest point to pick, most of the time, is this point right here. That's 0, 0. So our test point we are picking is 0, 0. And now, what we're going to do with that test point is plug it into the original inequality. Y is greater than x plus 1. So I'll rewrite it. I'll say y greater than x plus 1. And now plug 0 in for x and plug 0 in for y. And let's see if our inequality is true. So you'll get 0 greater than 0 plus 1. We get the inequality statement that 0 is greater than 1. Is 0 greater than 1? And that is false. So what that means is that our test point of 0, 0 happened to be false, which means that if you pick any other numbers below this line, they will also be false, which means that we don't shade the right side, we will shade the left side, the side above the line, because any point above that line is actually going to be true. So let's shade. Well, I guess before we shade, let me show you that a point is true. So let's pick another point. Let's pick this point. This point is 0, what is it? 1, 2, 3. 0, 3. Let's see if this point holds true. 0, 3. You'll plug it into the inequality above, which means I'll get 3 for y, plug in 3 for y, 0 for x. 3 is greater than 0 plus 1. We get 3 is greater than 1. Now, is 3 greater than 1 a true statement? That is definitely true, which means that we are going to shade above the line like we said when we picked the original test point. So all we have to do is shade. Let me use bigger colors. How's that? Shading, shading, shading. Throwing shade. And there you go. That's it. Okay, perfect. And that is what we're doing for these exercises. Now, we don't have to pick more than one test point, but I did it just to show you an example. Okay. Do I actually like, let me see. I wasn't happy with my shading. You get it. I'm just gonna fill all this in. There we go. Shaded. All right. Well, let's try it again. Example 2. 2x minus 5y is less than or equal to 10. Okay, so step 1, rewrite it as 2x minus 5y equal to 10. All right, now we have two options here. I can rearrange this into y equals mx plus b, or I can solve for the x and y-intercepts. Since I showed the method of using y equals mx plus b on the one above it, I'm going to show this by using X and Y intercepts now. So let's actually go with that method, because it could prove to be faster for you. So let's find the X-intercept first. And to find an X-intercept, we let Y equal 0, which means I'll get 2x minus 5 times 0 equal to 10. This will give me 2x equal to 10, divide by 2, and x equals 5. And of course, convert to coordinate 5, 0. Okay, then let's find the X-intercept. The Y-intercept. So you'll have for my Y-intercept, we let x equal 0, which means I'll have 2 times 0 minus 5y equals 10. That'll give me negative 5y equals 10. Divide by negative 5, and y will equal negative 2. Convert to coordinate. 0, negative 2. There it is. Okay. The next step is look at your inequality. We have a less than or equal to. This means that the line will be solid, right? Line will be solid. So we'll say step 2, we'll have a solid line. All right, then let's go ahead and graph. Okay, I'll plot the X-intercept of 5 and the Y-intercept of negative 2. Let's see, that's perfect. All right, I'll plot the X-intercept at 5. 1, 2, 3, 4, 5. And then I'll plot the Y-intercept at negative 2. Okay, and if you are graphing with the X-intercepts, those are the 2 truest points on the line, which means all you have to do is connect them. So let me see if I can get a straight line. Boom. And it's solid. That's perfect. Look at that. Okay. And now, the third step is to pick our test point. And again, we can pick a point above the line or we can pick a point below the line. And once again, since 0, 0 is not on the line, that is the easiest point to pick. So we'll pick 0, 0. And we're going to plug it in to the original inequality. 2x minus 5y less than or equal to 10. If I plug in 0, we'll get 2 times 0 minus 5 times 0 less than or equal to 10. And we'll get 0 is less than or equal to 10. Now, is 0 less than or equal to 10? That answer is yes. Therefore, this is true, which means that we will shade on the side where the points are true. This means that if 0, 0 is true, The rest of these points happens to be true. So we'll shade up. Okay. How can I make my shadings better? Let's see. Will the triangle work? No? Oh well. I think we get the point. So I'll shade. Up. There you go. Shade it. All right, good enough. Before I take too long on that, right? So that is shaded. Okay, so again, that's all we're doing here. All right. Example 3, same thing. But now we have a little additions. So we have the linear inequality. 24x plus 30y is greater than 7,200. And then we're given 2 more equations. X is greater than or equal to 0, and y is greater than or equal to 0. Okay. So we'll keep on with the first steps. Step 1 is change it into 24x plus 30y equal to 7,200. And then also make it x equals 0 and y equals 0, right? That's what these become. Okay. So we're going to plot, we're going to find the x and y intercepts for the first equation and then plot them. All right. Tongue-tied today. All right. So we'll look for the x-intercept, which means you set y equal to 0. And we know that'll zero out the y value for the first equation. So that'll just leave me with 24x equal to 7,200. And then I will divide 7,200 by 24 and get x equals 300. Convert to x-intercept at 0, comma, other way around, sorry, 300, comma, 0. All right. Next is the y-intercept. Let x equal 0. And that means it'll zero out the 24x, which will give us 30y equal to 7,200. Divide by 30, and we'll get y equals 240. Convert to y-intercept, 0 and 240. Okay, now on to these two equations. What type of graphs do these two equations make? And if you look at x equals 0, remember that x equals 0 is the graph of a vertical line. So this just makes a vertical line. And remember that y equals 0 we'll make a horizontal line. Okay, which means that, well, there's no need to find an x-intercept or y-intercept for these two equations. We just have to know what type of lines they make. Okay. So, yes. And then before I move on, let me explain what the restrictions mean when we have x greater than 0 and y greater than or equal to 0. Okay. So, these restrictions mean that x can only be positive and y can only be positive. So when we are graphing, we only really care about quadrant 1. That is it, right? We only want our shadings in quadrant 1. So this keeps us in quadrant 1. Okay. That's what those restrictions mean. That means we're stuck in quadrant 1. All right. Step 2, what type of lines do we have? All right. So for step 2, for the first one, we just have a greater than. So we're going to have a dashed line, right? For the last two equations, there's a greater than or equal to and a greater than or equal to. So for the last two, both lines will be solid. All right. So we're going to have one dashed line and two solid lines. All right, perfect. All right, now let's graph. Now look at my x value, 300, and look at my y value, 240. So let's make some appropriate intervals. I'm going to zoom in really fast here. Okay, so making the appropriate intervals, since x is in the 300s, I am going to spread out my x-axis, which means I'm going to make this value 0. I'm going to skip 1 and make this 100, 200, 300, 400, 500. And then, since my y value is 240, my y-intercept is 240, I can go by, let's say, what, 60s? Let's do that. And I think I can skip on that, yeah. So let's see, skip, make this 60, 120, 180, 240, and 300. So I'm just making the intervals appropriate. Okay. So now let's plot the x-intercept and the y-intercept since we made our intervals appropriate. And I'll plot the x-intercept, which is going to be at 300 and 0, which is right there. And then I'll plot the y-intercept, which is at 0 and 240, which is exactly right there. And then I will connect the line, but it's going to be dashed. Do they have a dashed line on here? No. So I'll just draw it by hand. Yeehaw. Okay. All right, so let's see. I'll zoom in a bit. Okay. Oh, way off. Let's see, probably better. So there's our dashed line. And now let's go ahead and plot our vertical line and our horizontal line. X equals 0. So there's our vertical line. I'll make it green. X equals 0 is the vertical line at 0. So I'll make a straight line one day, right? Here's X equals 0. And then let's graph the last one, the horizontal one, Y equals 0, which is a horizontal line. There's Y equals 0. Okay, and those were solid, right? Those are my solid ones. Okay, so we have graphed everything. Now the last thing to do is pick a test point, which means that we have to pick a test point above the green line, or how about a test point to the left or the right of the green line, a test point above the pink line or below the pink line, and a test point that is below the blue line or above the blue line. So let's find ourselves a test point. All right. Okay. So here's where these restrictions come into play. I said they keep us in the first quadrant. So the only line we are really worried about is the dashed line, right? So this means go ahead and just pick a test point above it or below it. And lucky for us, that test point happens to be 0, 0. So that's the test point we are going to pick. And like I said, that test point is, well, actually, that one's right on X equals 0 and Y equals 0. But those lines don't matter. The only reason they matter is because they keep us in quadrant 1. So we can pick 0, 0. All right. So 3, test point. We pick 0, 0, and we plug it into just the first inequality, which is 24x plus 30y greater than 7,200. Okay, now if I plug in 0, I'll get 24 times 0 plus 30 times 0 greater than 7,200. This means we get the statement 0 is greater than 7,200. Now, is that a true statement? And that answer is no. This is false. So, since 0, 0 was false, we get to shade on the opposite side, meaning we get to shade above the line. So this means that we are going to shade up. But since we are restricted to quadrant 1, our shadings will only remain in quadrant 1. There you go. Better. And that's it. That's all we do. All right, not bad. Okay. Word problem. On this one, we are going to make our own inequality. Okay. Labor costs for a farmer are $55 per acre for corn and $45 per acre for soybeans. How many acres of each crop should the farmer plant if he wants to spend no more than $5,000 on seed? Express your answer as a linear inequality with appropriate non-negative restrictions and draw its graph. Okay, so you see the little hints above. We want to translate English into algebra. So the words no more than mean we are going to use the less than or equal to symbol. And we said that we want to spend no more than $5,000 on seed. Okay, so our first step is let's go ahead and make this inequality. All right. There we go. Work with me in equality. Okay, so looking at the problem, we see that we want to spend $55 per acre of corn. So this means that let's go ahead and represent corn as X. So we're going to have 55X plus, and then we want to spend $45 per acre of soybean. So that's going to be 45Y. And then the farmer doesn't want to spend, he can't spend no more than $5,000, which means we're going to be less than or equal to 5,000. There it is. There's your inequality. That's all we had to make. And now we want non-negative restrictions. And when I say non-negative restrictions, that's going to be just like the last problem we graphed. To be non-negative means to be stuck in quadrant 1. So the non-negative restrictions are going to be X is greater than or equal to 0 and Y is greater than or equal to 0. These are your non-negative restrictions. Which also means it keeps us in which quadrant? It keeps us in quadrant 1. Okay. Well, now we have our inequality. Now we must find its X and Y intercepts and graph it and shade appropriately. And then we'll be done. Okay. So we'll call this step B. My goodness. We'll say step B. We'll find the X-intercept, which means we let Y equal to 0, which means you'll get 55X equal to 5,000. Go ahead and divide 55. And we will get 90.9, which we can round up to 91. Convert, you get 91, 0. Okay, and then find the Y-intercept, let x equal 0. And we'll have 45y equal to 5,000. Do 5,000 divided by 45. And we'll just get y equals 111 acres of soybean, right? And then convert 0, 1, 1, 1. Okay. Perfect. See, what type of lines are we going to have? Well, every inequality has a less than or equal to or a greater than or equal to. So all lines will be solid. So let's go ahead and graph. Look at my X-intercept, look at my Y-intercept, 91 and 111. This means for my X values, I'll go by tens. Why not? So I'll come down here and I'll say that this is 0, then 10. Whoop, don't skip. Actually, could I just go by 20s? Yeah, that'd probably be better. I'll say 20, 40, 60, 80, 100. That takes care of my X values. And my Y value goes up to 111. So why not? We'll still go by 20s. 20, 40, 60, 80, 100. Let me expand this a little longer. And there's 120. Perfect. Okay, let's go ahead and plot our points. All right, I'll plot the X-intercept first at 91. There's 80, in the middle is 90. So right there is fine enough. Y-intercept is 111. So there's 110. Right there is perfect enough. Okay. And then we'll just have our solid line connecting them. Close enough, right? Let me try again. Okay, so there's that. And now we'll plot our non-negative restrictions, which are just our vertical line and horizontal line that keep us in quadrant 1. Okay, so a little thicker. That's not X. Y equals 0. And then here is X equals 0. But of course, we are stuck in quadrant 1, and we only want to choose a point above or below the blue line, which means, again, our best friend, our best point to choose is going to be 0, 0. So that'll be step 4. We pick 0, 0 and plug it into the inequality we made, 55x plus 45y less than or equal to 5,000. Plug in 0 for x, plug in 0 for y, and we will end up with 0 is less than or equal to 5,000. Is that a true statement? And that is true, which means when we come back to our graph, we will be shading down, but our shadings will be contained just in quadrant 1. So there we go. Shaded. All right, excellent. So we made our own restrictions. We made our own inequality. And if the farmer wants to spend no more than $5,000 on seed, if he chooses any appropriate combo that is within this shaded triangle in quadrant 1, he would definitely be below his $5,000 range. Okay, excellent. I think that finishes 5.1. That is it for 5.1. So we are shading, shading, shading. Okay. (5.2), we are now going to graph a system of linear inequalities. So we will use the same steps from 5.1, the same exact steps on how to graph, get the X-intercept, get the Y-intercept. Then we are going to find the points of intersection between the two equations. These will be called corner points of the boundaries of the graphs. We will shade the set of points that satisfy all the inequalities simultaneously. The shaded region is called the solution region or feasible region. If a solution region can be completely enclosed in a circle, it is said to be bounded. If a solution region cannot be completely enclosed in a circle, it is said to be unbounded. All right, let's do it. So now we're given 2 equations. Okay. So we'll break down the first equation, 3x plus 4y less than or equal to 12. All right. So I'll change it into, not that, 3x plus 4y equal to 12. I will solve for the X-intercept, and I will solve for the Y-intercept. X-intercept, let y equal 0. That gives us 3x equal to 12. Divide by 3, we get x equals 4, which gives us the point 4, 0. All right. Then find the Y-intercept. We let x equal 0, which means I'll get 4y equal to 12. and y will be 3. So you'll get 0, 3. Okay. Then, second step, will we have a solid or dashed line? And for both inequalities, they are less than or greater than or equal to, so they will both be solid. All right. So 2. We're going to have 2. We'll have 2 solid lines. All right. All right. And then over here, let's look at, before we start graphing, let's look at the second inequality. And that is just going to be y greater than or equal to -3 is going to be the equation y equals -3, which is another horizontal line. Okay. Let's go ahead and graph and let's see, my x value is 4, my y value is 3, my other line is y equals -3. We can leave the intervals alone. They're going to be just fine. So I'll plot the x-intercept and y-intercept first for our first equation. And let's see. We'll be at 4, 0, which is there. And then we'll be at 0, 3, which is there. And this will be a solid line. All right. And then we will graph y equals -3. This means that at y equals -3, we'll have a horizontal line. So starting here, we have our horizontal line. Okay, and they are both solid. All right. The next step in the process is, after graphing both lines, let's find out where these functions intersect. Where do these graphs intersect? And if my graph is nice and neat, it looks like they intersect right here in this bottom right corner. And that point is going to be, what do we have? 1, 2, 3, 4, 5, 6, 7, 8, and -3. So this is going to be 8 and -3. So that is their intersection point. That is their corner point. Okay. And now, what we want to do is pick a test point, which means now we need to pick a test point above or below the green line, and we need to pick a test point above or below the blue line. Well, we can come at an agreement and say that our favorite point of 0, 0 happens to be below the blue line and above the green line. So we're going to make our lives easier and pick 0, 0. And this is going to be our test point. All right. I guess I should label this. I'll say 3. Our corner point is 8, -3. And then we go to step 4. Test point. We picked 0, 0, and we're going to plug that into both inequalities. So 3x plus 4y less than or equal to 12. I'll write that one first. 3x plus 4y less than or equal to 12. So let's test it in that function first. And if you plug in 0, you'll get 0 is less than or equal to 12. Is that a true statement? And that is definitely true, which means let's go to the graph. And since 0, 0 is true for the blue line, we are going to shade down, because we shade towards the true point, right? So shade okay, and now we're going to take that same test point of 0, 0 and plug it into the second inequality, y greater than or equal to -3. And the only thing we can do here is plug 0 in for y. And we'll get 0 greater than or equal to -3, which means, is that a true statement? And that answer is yes. This is true. Which means that since 0, 0 was true, and it was above the green line, we are going to shade up. So shade up. And there we go. That is all we have to do. Okay. All right. So much shading today, right? All right, next one. Okay. 3x plus 4y, I think, let me see. Can we do that? No. It was 3x plus 4y, 12, and 3x plus 4y less than or equal to 24. Okay. So example 2, we have 3x plus 4y less than or equal to 24, and we have those non-negative restrictions of x greater than or equal to 0 and y greater than or equal to 0. So all we really have to focus on here is just graphing 3x plus 4y less than or equal to 24. So let's go ahead and take care of that. Okay. So 1. 3x plus 4y equal to 24. And get your x-intercept. We said y equal to 0, which means you'll get 3x equals 24, and x equals 8. Here you get 8, 0. And then find your y-intercept. With x equal to 0, and you'll get 4y equals 24, divide by 4, and y equals 6. Repetitive process, right? 0, 6. All right. And then step 2, it looks like we have all less than or equal to's or greater than or equal to's. So in step 2, all 3 lines will be solid. Okay, now go ahead and graph. I have 8, 0 for my x-intercept, 0, 6 for my y-intercept, and those will fit on the actual graph. So we'll plot those. 8, 0, let's see. 1, 2, 3, 4, 5, 6, 7, 8, right there. And then 0, 6, 1, 2, 3, 4, 5, 6, right there. And now just connect. And then we will draw our non-negative restrictions like usual. And we know those restrictions keep us in quadrant 1. So that's fine. And then okay, excellent. So next is to find the corner points, the points of intersection. How many points of intersection do we have? So we have a point of intersection here, here, and here. So if we look closer, our points of intersection happen at 0, 0. It happens at where my y-intercept is and where my x-intercept is. So those are going to be our corner points. So we'll label that step 3. So our corner points are at 0, 0, 8, 0, and 0, 6. Okay. Last part is to pick a test point. So again, we don't really care about the green line or the pink line. We just want to pick a point above the blue, our blue line, a point above or below. So we can go ahead and again pick 0, 0. Let's pick 0, 0. All right. So 4. We pick 0, 0. And we plug it into the original inequality, 3x plus 4y less than or equal to 24. Plug in 0 for x, plug in 0 for y, you get 0 less than or equal to 24. Is that a true statement? Definitely is. So this is true, which means we always shade towards the true point. But since we have those non-negative restrictions, this means our shadings will be stuck in quadrant 1. So I'll do that. Let me erase this first. All right. And there it is. Okay, so similar to what we were doing in 5.1, but now we are wanting to find corner points. And I think it said find out whether we are bounded or unbounded. Well, since these shadings are stuck in quadrant 1, if I can draw a circle around my feasible region, my shadings, this means that it happens to be bounded. So this is bounded. If we look at the last one, since these arrows head off towards the left, the shadings will go on infinitely, which means I cannot draw a circle around them. This means that our feasible region will be unbounded. Okay, cool. Keep going, keep going, keep going. All right. 3. We now have a system of 2 equations, technically 4, but we know what the last 2 restrictions do. X greater than 0, y greater than or equal to 0, those keep us in quadrant 1. So we don't have to really worry about those. Again, the only thing we should take from that is they will keep our shadings in quadrant 1. Okay, so let's go ahead and graph 6x plus 3y and 3x plus 6y and find their corner points. So handle this all the same, right? All right, so say 1, I'll have 6x plus 3y equal to 24. Find the x-intercept. And find the y-intercept. So 6x equals 24. I get x equals 4. So we get 4, 0. I'm going to keep these colors the same since I'm graphing 2 lines now, right? 2 actual equations. So I'm going to say y-intercept, x equal to 0. And that means you'll get 3y equal to 24, divide by 3, and y equals 8. Which means we get the point 0, 8. All right. And then 2. I'll write the next one. 3x plus 6y equal to 30. And same exact process. Find your x-intercept, find your y-intercept. Three x equals 30, x equals 10. Y-intercept, X equals 0, 6y equals 30, y equals 5. All right, and then we get 0, 5. All right, there's our X-intercepts, Y-intercepts for both equations. 3. We see that all of these are less than or equal to or greater than equal to, so we know we'll have 4. Solid lines. So let's go ahead and graph. All right, so make that a little bigger. So I'll plot the blue line first, and I have an x-intercept at 4, and I have a y-intercept at 8. I will connect those two. And then I'll graph the second one, and I have a y-intercept at 10, an x-intercept at 10, which is there, and I have a y-intercept at 5. And then I'll connect those two. And then I will draw my non-negative restrictions. So and then the last one we'll do in black. All right. Well, there is a lot going on here, right? But I'm gonna make it easy. We wanna pick, first we'll shade, because there's a lot of corner points you see right now. All we really want are the corner points of the feasible region. So let's go ahead and shade, and then we'll find corner points. So let's go to step 4. Let's shade, and what we only want is a point below or above the pink line and below or above the blue line. And again, that point happens to be, well, our favorite point of 0, 0. So let's try it out. Okay. So 4. Test points, we choose 0, 0. And we're gonna plug it into both functions. I'll start with the first one. 6x plus 3y less than or equal to 24. If you plug in 0 for x and y, you'll get 0 less than or equal to 24. Is that a true statement? That is definitely true, which means that from the blue line, we will shade down. But since we have non-negative restrictions, our shadings will be stuck in quadrant 1. Okay, and then take 0, 0 and plug it into the second equation. 3x plus 6y less than or equal to 30. If you plug in 0 for x, you plug in 0 for y, you'll get 0 less than or equal to 30, which is again true. Which means that we will shade towards 0. So now we shade down, 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 down. Okay, so now our job is to look for corner points. And we only want the corner points of the feasible region. And the feasible region is where this shadings intersect. And the feasible region is what can be enclosed in a circle. So this means that we are going to have corner points. We're at right here, here, there, and there. That's where our corner points are going to be. So 3 of them are obvious. The first one that I pointed out, top left, that corner point is going to be the y-intercept for the pink line, which is 1, 2, 3, 4, 1, 2, 3, 4, 5, right? So this first corner point is 0, 5. The next obvious corner point is the very bottom one. 0, 0. The third obvious corner point is the bottom right. This one is the X-intercept for the blue line, which happens to be at 1, 2, 3, 4. So 4, 0. Okay. And then the next corner point, which if my graph is correct, it looks like it's going to be at 2, 4. So these are my corner points of the feasible region, and that's all we want. So for 5, we'll list our corner points. Okay, and we said what? 0, 5, 0, 0, 4, 0, and what did I say? 2, 4? Somewhere around there. I hope it's 2, 4. So let's say that my graph is not all that accurate. Could this corner point actually be 2, 4? The only way to make sure to verify that that corner point is actually 2, 4 is to take these two equations and solve them by elimination method. So that's what we're going to do. A little more work, I know, but I need to make sure that point is 2, 4. If it's not 2, 4, then we must correct it. So this is what we're going to have to do. We're going to solve it in a system of equations. So I'm going to say prove corner point 2, 4. Okay, that means I need the equations 6x plus 3y equal to 24. And 3x plus 6y equal to 30. Okay, let's solve this system, and we can get rid of x or we can get rid of y. It does not matter which one because both of them are 6 and 3 or 3 and 6. So I'll say, let me just get rid of x. So if I'm going to get rid of x, I'm going to multiply this whole equation by -2, which means I now have 6x plus 3y equal to 24. My new equation for the second one is -6x minus 12y equal to -60. Add them together, and your 6x's will cancel, and we will get 3y minus 12y, -9y. 24 minus 60, we get -36, which means if you divide by -9, y equals 4. Okay, that's one check. 4 is good, but now we have to check if the 2 is right. So take 4 and plug it into either the first equation or the second equation to prove it. And I'll just plug it into the first one. So we'll say find x, and I'll plug it into 6x plus 3y equal to 24. And you'll get 6x plus 3 times 4 equal to 24. And you'll get 6x plus 12 equal to 24. Move the 12 over. 6x equals 12, and x equals 2. Therefore, we were correct. That counterpoint is proven now to be 2, 4. So the only reason I did that is because my graph may look unclear, and I want to prove that intersection point of the blue and the red line of both equations is actually 2, 4. All right, so it's proved. Proved. We have our solution of 2, 4. Okay, excellent. Ooh, I know it's a lot, right? All right, well, it's good because we're on the very last one. All right, example 4. A manufacturing company makes 2 types of water skis, a trick ski and a slalom ski. The trick ski requires 6 labor hours for fabricating and 1 labor hour for finishing. The slalom ski requires 4 labor hours for fabricating and 1 labor hour for finishing. The maximum labor hours available per day for fabricating and finishing are 108 and 24 respectively. If X is the number of trick skis and Y is the number of slalom skis produced per day, write a system of linear inequalities that indicates appropriate restraints on X and Y. Find the set of feasible solutions graphically for the number of each type of ski that can be produced. Okay, so we know that there are 108 hours for fabricating altogether. And if we look, the trick ski requires 6 labor hours for fabricating, and the slalom ski requires 1 labor hour, right? No, let's see, 6 labor hours for fabricating. The Solomsky requires 4 labor hours for fabricating. So we have our first inequality, which means that down below, this should be 6x, 6 labor hours for fabricating the Tricksky, and then 4 labor hours for fabricating the Solomsky. And we're only given 108 hours total for fabricating. Okay, and then to finish the skis, the Tricksky requires 1 hour for finishing and 1 hour and then 1 hour for finishing on the slalom ski. So this is just 1 and 1. Okay, we have our linear inequalities. We know how to work them. Let's go ahead and graph. All right. And again, we treat these the same way as we did them all. So maybe we can speed through this, right? So first one is going to be 6x plus 4y equals 108. Find your x-intercept. Find your y-intercept. Here's 6x equals 108. Here, 4y equals 108. 108 divides 6. I get 18. 108 divide 4. I get 27. We get the point 18, 0, 0, 27. All right. 2. Same thing. Now you have 1x plus 1y equal to 24. All right. Get your x-intercept. Get your y-intercept. And you should get x equals 24 and y equals 24. All right. Which gives me 24 and 0 and 0, 24. We have non-negative restrictions. We have our inequalities. They all have the less than or equal to's or greater than or equal to's. So step 3 means all lines will be solid. You'll have 4 solid lines. All right. So 3. Okay, so let's go ahead and graph them. Let's look at our intervals. 18, 27, 24, 24. We can go by what? 3s? I think so, right? Yeah, we should be able to go by 3s. So let's do that. Here's 0, 3, 6, 9, 12, 15, 18, 21, 24, 27, 30. Same thing here. 3, 6, 9, 12, 15, 18, 24, 27, 30. Okay. Perfect. There's my intercepts. I'll graph the blue one first. I have an x-intercept at 18, which is here, and an y-intercept at 27, which is there. Let me connect, do my best. And then I'll draw the red line. I have X-intercept and Y-intercept at 24. That makes it easy, right? Okay. So 24, 24. Okay, and then I'll put the non-negative restrictions, of course. I'll just make them both green. How's that? And all we know is that, or what we know is that the non-negatives keep us in quadrant 1, and we want to find the intersection points, but we only want the intersection points at the feasible region, so let's go ahead and shade first, which means that we want to point below or above the blue and red line, and guess what our favorite point is? 0, 0. So we will pick our test point and plug it into both functions. They are both less thans, okay. So 4 test points, 0, 0 into 6x plus 4y less than or equal to 108. Plug in 0. You'll get 0 less than or equal to 108. That is true, which means shade down. And then again, I'll plug it into the red one. Into x plus y less than or equal to 24. 0 less than or equal to 24. True. Shade towards 0, 0. So shade, shade. And then shade as well. Okay, our feasible region is what can be circled, right? And it looks like, and it's where our shadings intersect. So we want to find the corner points now, which means it looks like we have corner points here, there, here, and exactly here, where the two lines intersect. Okay, so the obvious ones are, of course, the x and y-intercepts and our favorite point of 0, 0. This one is 18, right? 18 and 0. This point is, I'll do it from the other side, is 0, 24. And this point, if our graph is good, I think it might be 6 and 18. But we're going to have to prove it because I'm not sure. Corner points, we said 0, 0, 0, 24, and 18, 0. And then I said 6 and 18. Let's see if I'm right. We have to prove it though. And then I'll say 6. So I'll put the equations on top of each other. 6x plus 4y equals 108. And x plus y equals 24. Right? Is that right? Yeah. All right. Solve the system. Get rid of x, get rid of y, up to you. Let's get rid of y because it's the smaller number. So I will multiply the first equation by -4, which means I'll have 6x plus 4y equal to 108, -4x minus 4y equal to 24 times 4, 96, negative. All right. Add these, and we'll get 6x minus 4x, 2x. 4's cancel. 108 minus 96. We get 2x equals 12, and therefore x equals 6. Hey, look at that. First part of the point proved. Now we just need to find y. We're going to use the easiest equation up there. X plus y equals 24. Plug in 6. 6 plus y equals 24, and y is definitely going to equal 18. This is definitely proof. Whew, doggy. All right. And that is linear inequalities. All the colors. All right. That finishes up 5.1 and 5.2. I hope you had fun. It definitely was a lot. But it's everything we've been doing so far. We've been doing linear equations. We've done linear inequalities. We've done a system of equations. We've done graphing. So it's one big lesson molded in, right? Okay, but that is it.